Hello viewers, subscribers, and students. Here is another example on beams, indeterminate beams with support settlements aided with RISA. And the technique. This problem has been solved by other methods such as the three-moment equations. And these were the results: slope deflection equations, results for moments at B and C, which were solved accurately. And by moment distribution method, you just uh, explore my YouTube channel, particularly on structural analysis, by the playlist there, solve problems in structural analysis or structural theory, as well as in matrix structural analysis. So this is the combination of the concepts on matrix and with the aid of this software RISA, which I have just discovered the technique. So I'm going to share this with you. So we have support settlements, and therefore the fixed moment due to these support settlements alone, sideway, would be negative 6EI delta over L square, where EI is 200 times 10 to the 6 kilopascals times 500 times 10 to the 6 mm to the fourth divided by 1000 to the fourth to convert it to meter to the fourth, and the unit becomes kilonewton meter square, and it is 100,000 kilonewton meter square to be consistent. So delta for segment AB is positive because the sign convention for slope deflection equation is when the chord rotates clockwise like this, then delta is treated positive as well as the slope positive. And delta is simply the difference between 15 and 8, and it is 7 mm, but we have to convert it to meter here. So positive 0.007 divided by 8 square, and we'll obtain negative 65.525 kilonewton meter. Since this is negative, it is counterclockwise by slope deflection equation. But remember that in the universal sign convention, counterclockwise rotation, counterclockwise moment would be positive, especially in softwares. So as I said, because this is slope deflection equation concept, the negative 65.525 is treated counterclockwise as shown. So counterclockwise also here. Fixed moment BC due to side sway or due to settlement is equal to fixed moment CB due to settlement also. And it is negative 6EI. Then delta is treated negative this time because the chord BC rotates counterclockwise, and delta is 15 minus 10, so 5 mm. So negative 0.005 divided by L square, 5 square, and it is positive 120 kilonewton meter. So this is interpreted clockwise. So 120 clockwise, 120 clockwise. Then for CD, which is equal to DC, the rotation of the chord is again counterclockwise, so delta is treated negative. 10 minus 6 is 4 mm, so negative 0.004, negative 6 EI, negative 0.004 over 6 square, 66.667 kilonewton meter. And we cannot input 200 over 3. This is 200 over 3 in this software RISA. It should be in decimal and to 3 decimal places in RISA. So we have to apply clockwise couple again due to settlements 66.667 and 66.667. We then compute the fixed end force due to these couples. So summation moment B equals 0. This should be upward so that the moment is clockwise and equated to this counterclockwise couple. So FAB times 8 equals 65.525 times 2. So 65.525 times 2 divided by 8 will get 16.381. And since it is upward here, on BA it should be downward because it is due to the couple, not including due to the weight. So this is fixed force due to the couple. Then 16.381 downward here. For BC, the fixed force should be downward so that it will produce counterclockwise movement about C because these couples are clockwise couples. So 48 times 5 equals 120 plus 120, or 120 times 2 divided by 5, you'll get 48. So for CB, it should be 48 upward because this is 48 kilonewtons downward, 48 kilonewtons upward. Finally, for CD, the fixed force should be downward because the couples are clockwise. So fixed force times 6 equals 66.667 times 2. So you'll get 22.222 kilonewtons downward here. So on the other end, it should be upward. We then input this data in RISA together with the loads. And remember that the nodal forces, the nodal loads, are opposite to this fixed end forces. So 16.381 should be now be downward or negative 16.381, and 65.525, which is counterclockwise, should be clockwise. And in that software, clockwise moment would be negative. So like here, we have this is negative 16.381 downward, and we have a couple which is clockwise, so that's why negative 65.525. At B, 120 clockwise minus 65.525 will obtain the net fixed end moment of 54.525 clockwise, but since the nodal load is opposite to that, so we have counterclockwise, positive 54.475 in the software. So 54.475 is the difference between 120 and 65.525. Then the force, 16.381 plus 48 is 64.381. Since these are downward fixed forces, the nodal load is upward, and 64.381, the sum of these two. Then for the next joint C, let's begin with the couple first. 120 clockwise plus 66.667 clockwise is 186.667 clockwise. That's the fixed end moment. But the load is opposite to that, counterclockwise, so positive in the software, 186.667 kilonewton meter. Then for the load, fixed end force, 22.222 minus 48, so downward minus upward, negative. So negative because the load should be opposite. The net load, fixed end load here is upward, so the load should be downward. So again, the technique is make downward negative positive, then upward negative. 22.222 minus 48 is negative 25.778. And lastly, we have negative 22.222 down here. So that's negative 22.222 downward. And the couple, this is clockwise, so counterclockwise, positive 66.667. Then in the menu in RISA, we then press solve, and this will be the results. So we have the joint reactions, node 1, 2, 3, and 4. So therefore, the reaction at node 1 is equal to 99.661 kilonewtons. And the reaction at B, 155.259 kilonewtons. reactions at C 43.776 kilonewtons upward, and at D the reaction is vertical reaction is 65.314 kilonewtons upward. Then it is the moments at A and D that are final 0, 0, 0, 0, but the internal moments at B and C should be adjusted by adding these fixed end moments. So for instance, the results for the moment at B for member 1 and end of member 1, beginning of member 2 is negative 218.706. Then we add 120 because the moment at B is moment BC. And since this is clockwise, 120, so plus 120, negative 218.706 plus 120, we have negative 98.706 as compared to negative 98.677. Of course, there's a small discrepancy because here the loads are limited to 3 decimal places, whereas in 3-moment equations, slope deflection equations, we solve accurately the fixed end moments. The values are in fractions, so that's why we get these accurate results. But this is practically equal to that, of course. Then MC is MCD, and it is equal to, this is the moment at C, left and right. So negative 106.778, then plus fixed end moment of 66.667, we'll get negative 40.111 as compared to negative 40.119. So practically they are equal. So this is the final moments, moment at A0. B and C internals must be adjusted by very simple process only. We just add the fixed moments. That's it for this video. I hope that you were able to follow and understand the explanations. I also solved previously problems with support settlements with the aid of RISA.